The main intention of this video is to define electrolytes, the types that there are, and then to link the concept to acids and bases and to show how they are all related to each other. On the left-hand side, I have listed some terms that will be helpful for you to know ahead of time going into this video so that you can get the most out of it. And then underneath of that is a general outline for how I'm going to proceed. And just to let you know, WE stands for weak electrolyte and SE stands for strong electrolyte. We're going to start with some definitions. An electrolyte is a substance that is going to dissociate in water to produce an aqueous solution of ions. I really want to stress that word dissociates, hence the caps and the underlining. When you think electrolyte, I want you to think dissociation. Okay, the opposite of that is going to be a non-electrolyte, which is going to be a substance that does not dissociate to produce ions in aqueous solutions. So let's work on putting this word into context by looking at a couple of examples. Again, I want you to focus on that term dissociate. Now, if you've ever seen table salt, what you have seen is the solid version of NaCl or sodium chloride. Now, remember, sodium chloride is an example of an ionic compound because that sodium has a plus charge associated with it, and that chlorine has a minus charge associated with it. Now, when you put it into water, it seems to disappear, or it dissolves into that water. What's really happening is that those ions are now separating or dissociating so that you now have an individual Na plus ion and a Cl minus ion. The AQ that I have written after each of these ions stands for aqueous, meaning that these ions are in water. Most electrolytes that you come across are going to be ionic. However, there are molecular electrolytes out there. An example of that is HF or hydrogen fluoride. The reason it's molecular is because there is a covalent bond that exists between that hydrogen and that fluorine atom. That covalent bond implies that there is a sharing of electrons between those two atoms, whereas in the sodium chloride, there is no sharing of electrons. It's simply their opposite charges that is attracting them to each other. So don't write that single bond between them like this. I feel really icky even just doing it like that. So don't write it like that. Now, if you were to put this hydrogen fluoride into water the way that you did with the sodium chloride, you're also going to have a dissociation, and that dissociation then gives you H plus ion and then a fluoride ion. Just like with sodium chloride, we are in water with this particular example, so we're going to put the AQ or aqueous after each of these ions, and it satisfies all of the requirements for that particular definition. So HF or hydrogen fluoride is also an electrolyte. I want to go over a few more examples because these are going to be compounds where the ions are not going to be one-to-one proportions. The first example that I have here is sodium sulfate, and as you may remember, sulfate has an overall 2- charge, which means that there needs to be 2 of the 1+ sodium ions in order to balance out that sulfate charge. So now when you put this into water, what you're going to get then is going to be 2 sodium ions for every 1 sulfate ion. Another example is magnesium hydroxide. Magnesium is a group 2 element, so it most commonly forms a 2+ ion. Since hydroxide is the counter ion here, hydroxides have an overall 1- charge, which means that we need 2 of them in order to balance out that magnesium. So when you have this in water and it dissociates, what we get is 1 magnesium 2+ ion, and then we get 2 of the hydroxide ions. Notice that the number 2 is written as a subscript for sodium sulfate, and that it is in the coefficient when written on the right-hand side of that arrow. And the reason for that is because on the left, it is written for an ionic compound, whereas on the right-hand side, we are now talking about individual ions because the compound has dissociated or has separated. So look at magnesium hydroxide, the same thing happens where that 2 is subscripted because we are a compound, and then on the right-hand side, it is now a coefficient because it is now an individual ion. So there are 2 individual hydroxide ions that we got from the 1 magnesium hydroxide ionic compound. The next example is acetic acid. If you've ever smelled vinegar, then you have smelled acetic acid. And I'm going to quickly just draw the structure for you here, just to show you that it does contain covalent bonds, which is what makes it a molecular compound. And in order for it to be an electrolyte, again, it needs to dissociate into ions. So what's going to happen is this hydrogen that you see in the front here is going to become an H+ ion. And then the rest of the compound is going to be left. It's going to be C2H3O2-. And so this is an acetate ion. You will also see acetic acid written as CH3COOH. And similarly, it is the end hydrogen rather than the one that you see at the beginning that's acidic, or that's going to be donated, or that is going to dissociate. The reason why you might see acetic acid written this way is because it has something called a carboxyl group. And so that refers to that COOH portion of that molecule. In the lower structure, I'm going to box what this represents here. So it's going to be that carbon, and then one oxygen, the second oxygen, and then the acidic hydrogen that is there. Similar to sodium chloride, sugar also dissolves when you put it into water. The difference is that when sugar goes into water, the structure doesn't change. This brings me to a point that I'd like to make, which is that just because it dissolves does not mean it dissociates. The discussion of why both of these materials will dissolve in water but are not both considered electrolytes is something that will be discussed in depth when talking about solubility of compounds. One of the properties of a solution that contains electrolytes is that it is capable of conducting electricity. How well it conducts that electricity is dependent on how strong the electrolyte is. The strength of an electrolyte is directly proportional to the extent of dissociation that occurs for that particular compound. Therefore, a strong electrolyte, which I'm going to abbreviate SE, is going to be one where the majority of the compound, when you put it into water, is going to be dissociated. An example of that is going to be sodium chloride, NaCl. A weak electrolyte, which I will abbreviate WE, means that when you put that into water, only a small amount of that compound is going to dissociate. I'm going to walk through the examples and assign strength of electrolyte for each one, starting with sodium chloride on the top left here. I said that sodium chloride is an example of a strong electrolyte. That means that the majority of this compound dissociates when it's in water. So these values are going to be arbitrary, but let's say that less than 1% stays NaCl and greater than 99% of it becomes the ions Na+ and Cl-. Hydrogen fluoride is an example of a weak electrolyte. This means that only a small amount of that compound is going to dissociate into the ions, while the majority of it will stay in its compound form, HF. You might see this represented using something called a double-headed arrow rather than a single-headed arrow, because the single-headed arrow typically implies a complete reaction or a complete process. And since we know by definition that this is not the case for a weak electrolyte, the double-headed arrow simply means that not everything is turning or dissociating into ions. The correlation between the strength of the electrolyte and how well it conducts electricity is that the stronger the electrolyte, the better it conducts electricity. So in this drawing that I have below, if in this beaker we had a solution of sodium chloride, most, if not all of that sodium chloride would exist as Na+ and Cl- ions. And therefore this solution would be very good at conducting electricity, and that would result in a really bright light bulb as it completes that circuit. If we were to replace that sodium chloride solution with a hydrogen fluoride solution, you would have some ions in solution, but it wouldn't be very many. And so because there is the presence of ions, it can conduct electricity, but because the number of ions in solutions is so much lower, it would not be very good at conducting electricity. That light bulb would go on, but it would not be nearly as bright. In fact, it would be kind of dim as a result of that. So when you think weak electrolytes, think about it as a weak conductor, and you can have that visual of a dim light bulb. Now let's replace this solution with a sugar solution or glucose. What you would see is that the light bulb would not turn on at all, and that's because sugar is a non-electrolyte, meaning that it does not dissociate to generate ions, so there are no ions to be able to conduct any electricity. So when you think non-electrolyte, think non-conducting, and then you can visualize that with a dark light bulb. As I go through the rest of these examples, it may be helpful to recall the solubility rules regarding ions, especially those that don't have exceptions. The reason being is that ionic compounds that contain those ions are always going to dissociate in water, and that means that they are going to be strong electrolytes because they dissociate nearly completely. So those again are group 1A cations, ammonium, nitrate, perchlorate, and the acetate ion. If we look at this first one, sodium sulfate, on that second column there, it contains sodium. Sodium's a group 1A cation, therefore this is a nearly complete dissociation to generate a number of sodium and sulfate ions. So this is going to be a strong electrolyte. Magnesium hydroxide is a little bit more complicated because neither magnesium nor hydroxide is on that list. The general rule about hydroxides is that it's almost always insoluble unless it's paired with one of those without an exception, the that I have listed below. And so this is going to be a compound, since magnesium is not on that list, magnesium hydroxide is going to be one of those that does not dissociate completely. And so this is going to be a weak electrolyte. Finally, acetate, when it is in an ionic compound, is always soluble, but here acetic acid is a molecular compound. So even though you're getting an acetate ion out, this is going to be a weak electrolyte here. These examples here have a mix of acid, base, and neutral compounds. HF, because of its ability to donate an H+, is considered an acid. It's hydrofluoric acid. Acetic acid also donates an H+. Magnesium hydroxide we consider a base because it donates an hydroxide ion OH-. I'm a pretty visual learner, so things like flowcharts can really help me see how the terms are all connected to each other. In this case, the first question that you can ask yourself is, does this substance dissociate in water? And if the answer to that is no, then we know that we have a non-electrolyte. If it does, then we have an electrolyte. Once you determine that the substance is an electrolyte, the next question that you can ask is, does it dissociate completely when you put it into water, or does the majority of it dissociate? And if the answer to that question is yes, then you have yourself a strong electrolyte. If the answer to that is no, then you have a weak electrolyte. We can get even more specific and ask ourselves whether or not that particular substance forms an H+ ion. That will help us identify whether or not it's an acid. So if it's a strong electrolyte and one of the ions it forms is an H+ ion, then it correlates with a strong acid. If it's a weak electrolyte and one of those ions that it forms is an H+, it's going to be a weak acid. And if there is no H+ ion formed, it simply is just not an acid. From there, if something is not an acid, the possibility exists that it could be a base, and the qualification for that would be whether or not it formed hydroxide ions or OH- ions. If it's a strong electrolyte and it donates OH- ions, then you have a strong base. If it's a weak electrolyte and it donates OH- ions, then you have a weak base. If you have a strong electrolyte, but it doesn't donate H+ or OH- ions, then we would consider that to be a neutral compound. Hopefully what you can see from this flowchart is that if you're a strong base or a strong acid, you're also a strong electrolyte, and that if you're a weak base or a weak acid, you're also a weak electrolyte. And this is always going to be true as long as those acids fall under the Arrhenius definition of acids and bases. These neutral complexes that are at the bottom here, although neutral, They are not designated acid or base, but they're still strong and weak electrolytes. We can test this flowchart by looking back at those examples that we had previously discussed. So if we look at sodium chloride, if we ask, does it dissociate in water to form ions? Yes, it does. It is an electrolyte. Is that dissociation complete? Yes, it is a strong electrolyte. And then does it form H plus ions? No, so it's not an acid. And then does it form OH minus ions? No, so it simply is a neutral compound considered a strong electrolyte. Next up is hydrogen fluoride. It dissociates, so it's an electrolyte. It does not dissociate completely, so it is a weak electrolyte. It does form H plus ions, so it is a weak acid. Then we have sodium sulfate. It does dissociate in water, so it is an electrolyte. It dissociates completely because it has a group 1A cation that has no exceptions. Therefore, it is a strong electrolyte. It does not form any H plus ions, so it is not an acid. It does not form any OH minus ions, therefore it is a neutral compound that's considered a strong electrolyte. Magnesium hydroxide will form ions when you put it into water, so it's an electrolyte. But remember that it's not very soluble in water, so most of it is going to stay magnesium hydroxide rather than the ions, so the dissociation is not complete. It is a weak electrolyte. The ions it forms does not include hydrogen or H+, so it is not an acid. However, it does produce OH- or hydroxide ions, therefore it is a weak base. Acetic acid will dissociate. It's an electrolyte. Again, it's one of those that does not dissociate completely. It is a weak electrolyte. One of the ions it produces is an H+ ion, so it is a weak acid.